From low temperature lab at Aalto University, Finland. Here are my co-authors. Today I will present you a new state of matter, which is mobile and soft solid realized by helium-3 adsorbed on the nanotube. Here are our sponsors. Please interrupt me anytime you have question. So the outline of my talk is as follows. I will give a brief introduction to the quantum solids and say about proposals to observe in such quantum solids mobile vacancies at low temperatures and even supersolidity. Then I will continue with experimental details. I will briefly say a few words about what nanotube is, how we feed it with helium, and how we measure its mechanical properties. Then I will explain the results which we have obtained. Basically, the main result is that we see three distinctly different phases at low temperatures, one of which is completely new, was not ever observed. And I will give interpretation of these phases so that at low densities, at low coverages, we have liquid gas coexistence as usual in 3D. And at elevated densities, we enter the 1/3 solid, which is well established. This is stiffest phase on the carbon nanotube. But when we increase density even further, we obtain that the stiffness of the solid drops, and we see something like mobile solid, which is soft at densities higher than this stiff one. And the interpretation, what we give to this phenomena is that we form dimer solids. Dimer solid, solid made of bosonic dimers, which contain final amount of vacancies even at low temperatures due to the mismatch because the carbon lattice and the helium lattice. Then we'll speak about a little bit about theory of this new solid state. We show how the dimerization of atoms occur. We will see how mismatch creates ground state vacancies, which are then properties of the ground state and topologically protected. So we don't need to create them by any means, they're always there. And if this vacancy is delocalized at low enough temperature, we see this mobile gliding solid. And I will also discuss perspectives of supersolidity in such state. Okay. So what is supersolidity? In quantum crystals, quantum means that amplitude of 0-point motion is comparable to the lattice spacing. Vacancies delocalize at low temperatures, and they form a gas-like system. Due to motion of these vacancies, a mass flow inside the solid is possible, like in a fluid. But at the same time, the translation symmetry is preserved, like in usual solid. So this is a phase which has properties of fluid and at the same time properties of the solid. On cooling even further, vacancies should boson condense and providing not just a mass flow, but super flow of mass. And this is called supersolidity. This was first suggested by Andreev and Lifshitz in 1969. So basic thing is to realize that delocalized vacancy which is delocalized over the whole crystal sample is actually the ground state of vacancy. In order to localize vacancy, you need finite energy. This is very clear from this picture of the particle in the box. So the lowest energy of the particle in this box is proportional to the square of the lowest wave vector, which of course is possible for, and then in the larger space, the lowest energy is lower. So this is the ground state, and to localize particle vacancy, you need finite energy. So delocalized vacancies are ground state properties in quantum crystals. In year 2012, Roth and Barana applied quantum Monte Carlo analysis to the two-dimensional system of helium atoms, helium-4 atoms in this case, where artificially the vacancy was introduced, so that the number of atoms which they allow was smaller by one than the possible sites. And we see that at 1 Kelvin, the vacancy is very well localized. You can always point it. And at 0.5 Kelvin, already not so good, not so well localized. It's somewhere, it's here and here. And finally, at 0.2 Kelvin, you cannot say where it is at all. Just at each atomic site, there is a finite probability to find the vacancy, not the atom. So it's delocalized. And so this is a brilliant confirmation of the suggestion by Andreev and Lifshitz. Since 1970s, there was intensive studies in order to observe supersolidity, to observe zero-point vacancies. Unfortunately, in 3D solid helium, no zero-point vacancies have been observed. And moreover, the energy have been calculated by many ways to be of the order of 10 Kelvin. So below 1 Kelvin, there is exponentially small number of vacancies. So what about if we lower the dimension and try to stabilize vacancies by means of topological restrictions, which must be possible in the lower dimensions? So this was introduction about quantum solid and delocalized vacancies and supersolidity. Now, technical details. What is a carbon nanotube? If you take usual graphite, it consists of very symmetric C6 planes, which are very weakly coupled one to another. There is very weak van der Waals, which allows to separate them by means of putting the gas, then heating this, and this planes becomes detached. And finally, you cleaning, you operating this gas, and you find some flakes of this C6 plane, more or less so that this is graphoil or exfoliated graphite. If you take a single plane, a single flake of this graphoil, this is graphene. If you now take a piece of this graphene, roll it out, and glue, you form the nanotube. They can be armchair, zigzag, or chiral if the symmetry, like if you need to move up by a couple of atoms to for the rotation of 2-pi rotation. Okay. So experimental setup. We have a sample cell inside the copper nuclear stage. We have a sinter to good heat exchange between the copper coolant and the sample helium. We have a suspended nanotube, and we have a quartz tuning fork, because it also absorbs helium, and we can somehow control what's going on the nanotube. There is evident difficulty that on nanotube, if you have monolayer or submonolayer, you have only a few thousand of atoms on it, and you cannot control such a small amount of atoms. That's why we have a graphoil ballast, which has about 5 square meter effective area. And then we suggest that the absorption energy is nearly the same for graphoil and for the nanotube. And then if we put finite amount of helium, it will divide itself in proportion to the area of the graphoil and nanotube, and then we can easily operate and feed the nanotube with helium. So how we measure it? So this is a suspended nanotube, and we excite it with high RF voltage. And this RF voltage is frequency modulated, as you can see. And because carbon nanotube is not linear element, because its resistance depends itself on the applied bias voltage, then there appears a low frequency component exactly on the modulation frequency. And this has it has a usual Lorentzian, but differentiated with respect to the frequency, because it's not direct measurement at high frequency, but frequency modulation. So here F0 denotes the resonance frequency, and gamma is the width of the resonance or dissipation. So how we measure the coverage, the density of helium adsorbed on the nanotube? We were using the value of the shift of the central resonance with respect to vacuum one. And we measured this in the liquid, where we did not affect any stiffness effect from the helium, but only additional mass, which we measure. So then everything is really known. So this is a change of frequency with respect to the relative change of the frequency with respect to the vacuum. And this is if we neglect the stiffness in the liquid phase, then it's just proportional to the relative mass change. And here comes density of helium, which we want to know, and known density of helium or of carbon. So this is the formula what was used to measure the density of adsorbed helium. Now I go to results. So basically, we saw 4 kinds of transition. At lower densities, as I said, at lower densities and at lower temperature, there is a liquid-gas coexistence. And in this coexistence, liquid fraction, liquid clusters are mostly on the ends of the tube. That's because the ends of the tube are quite rough, and there is always some amount of solid helium, and then the liquid tends to attach to this. When we warm up above the critical temperature, the liquid gas coexistence transforms into the uniform fluid, and then this liquid clusters arrange uniformly over the tube, and effective mass of the tube increases. That's why there is a sharp decrease of the resonance frequency. Most of the transitions were quite sharp, but sometimes it's actually quite high density already, close to the solid. And maybe because of this, it's not so sharp, but as I said, 90% of the transitions are quite sharp, and accuracy of TC determination is quite high. When we increase density further, we enter to the solid regime. Solid provides additional stiffness to the tube. As one can see, this is the resonance frequency. It's proportional to spring constant divided by mass. So if we have if we have increase of the stiffness of the spring constant, we have increase in the frequency. That's what's happening here. This is, by the way, almost exactly the density of this famous 1/3 phase. And this is quite large, a few percent change of the resonance frequency. So fine, but when we increase the density even higher, this stiffness, this additional stiffness due to solid disappears, leaving only this peak, so that the solid trace can be continuously followed from the solid, which we call gliding solid, to the liquid. So this new solid phase has the same stiffness, or basically zero stiffness, like a fluid. So we were really quite puzzled with this, but when we increased density even further, the new confirmation comes that at some point the stiffness appears by jump, so that we enter from this mobile soft solid to the normal solid at these intermediate temperatures, which then melts to the uniform fluid. So, and to say so that one trace took typically 1 day, so it was quite a long measurement, as we obtained 40 or 50 traces altogether. And these are only good traces, some were not. So and then we plot this phase diagram. So this is lower density, lowest density where we have liquid plus gas coexistence, which transforms to the uniform fluid above the critical temperature. So this is a fit with van der Waals equation, this line here. And it fits quite well, I would say. So this, here I illustrate this phase, so that there is a liquid cluster and a rarefied gas. So then we have this stiff 1/3 solid here, and there is a quantum phase transition to the so-called gliding solid. And this is when at higher temperatures, this gliding solid turns to normal, which then melts to the liquid, to the fluid. So here I illustrate 1/3 solid. 1/3 means that every third of carbon hexagon is occupied with helium. And this gliding solid we attribute to the dimer solid, which consists of the bosonic dimers with vacancies. So here I again illustrate this 1/3 phase and 2/5 phase suggested by Greyhall. In addition to this dimer phase, we also suggest a more symmetric, also dimer phase at the coverage 3/8. And at even higher, this is basically the maximum coverage for monolayer helium on graphite or on the nanotube. These dimers, they come quite naturally. If you look at this 1/3 phase and you want to add more atoms and still remain in the commensurate phase, you necessarily end up with dimers. So there is no other way. Now, if we look at this flake and we try to form the nanotube from it, so we roll it about horizontal direction and glue, we see that generally we will have a mismatch because the lattice period of helium is 2 in this direction and even 4 in this direction, even 5. Okay, so mistake. So only in the 10% cases, the helium lattice will match carbon lattice or vice versa. And if we look now at this, so this lattice on top part would prefer to have dimers also here and here and here. And the lower lattice would prefer to have dimers here, here, and here. But this is like this, assume that there are 4 atoms in line, and this is not energetically favorable. So it prefers to create these vacancies, which are topologically stabilized, and they have zero excitation energy. They are always there. So topologically protected vacancies. So this is a value of the jump at the transition. And this is at low coverages, and this is not the fit. This is a calculation, because once we know the critical parameters of this system from the phase diagram, we can simply calculate how much helium is near the ends and integrate the effective mass and obtain this curve. So it's not a fit. It's calculation with no fitting parameters. In the solid, we have the largest jump corresponding to the largest additional stiffness produced by helium at exactly 1/3 coverage. And exactly when we start, when we enter the dimer solid, immediately we see the drop of this jump value, which means that there is no stiffness, no additional stiffness produced by this phase. Okay, this was about mechanical properties of helium. But we can measure also thermodynamical properties of helium. This is because the center of frequency depends on the stiffness of the spring constant, which in turn proportional to the tension of the tube. And the pressure of helium contribute directly to the tension. So by following resonant frequency far from the transition, we follow the pressure. So we follow it as a function of temperature. So basically this is additional pressure due to absorbed helium, arbitrarily shifted. We know from one-dimensional formulas that pressure of the system is proportional to the T square. Pressure is energy density, energy proportional to T to the force, and pressure proportional also T to the force. In case of 1D, it's T to the square. And that's what we see at densities not very high, which are corresponding to the 1/3 normal phase. These are indeed look like square dependence on temperature. But when we enter the dimer phases, abruptly this quadratic behavior changes to linear. So I fitted this curve, and there were many more with this power dependence. And this is the exponent gamma observed from the fit. So it's a little bit above 2 and almost exactly 1 in the dimer phases. That means that the system doesn't support phonons. So it's not elastic at all. It rather follows the ideal gas relation, which could be attributed to this delocalized vacancies, weakly interacted. So dissipation is another important parameter what we can observe from the resonant curve. Helium creates additional dissipation to the tube. Why is that? Because helium, when nanotube is moving, this is a cross section, it's always lagging behind nanotube, and there is always relative motion between the nanotube surface, nanotube atoms and helium atoms. And this can be expressed as a mobility mu times inertial force, which is just mass of helium and acceleration. And if we now calculate the dissipation power is proportional to the force times V, which is F square and mobility. So the larger the mobility of the phase, the stronger the dissipation. Let's don't care about this. I have not much to say about this, but squares correspond to the normal solid. And as one would expect, the normal solid is more stiff and the dissipation is smallest. Here is dissipation in the low temperature phase minus dissipation into the liquid for easier comparison. we see that all squares, all normal solid data have a lower dissipation than in the liquid. But these red diamonds are for gliding solid, and we see that it has the same dissipation as liquid, and in many cases even much stronger dissipation than the liquid. So we can say that this gliding solid is even more mobile than the liquid. Oops. Okay, enough. Now a few words about, sorry. About transitions themselves. Are they first or second order? At first sight, it's really a stupid question because everybody knows that melting is the first order transition. There is strong latent heat. This is the strongest transition what one can imagine. But if we look more carefully at this Clapeyron-Clausius relation for the slope of the coexistence curve or the melting curve, it's proportional to the latent heat divided by change of the molar volume. In the case of 2D, we should replace change molar volume to the change of the molar surface. This is not entropy, this is surface. But in 2D, the atoms occupy all available surface. So when you go through transition, when you melt the solid, or if you have transition between two solids, you have delta S equals 0, and then you have latent heat also 0. So all transition in 2D are of the second or higher order, except for the lower densities where we have not uniform configuration, but liquid clusters. And that's what was observed by Bretz and colleagues in year 73, when they measure heat capacity of helium on graphite, of helium, both helium-4 and helium-3. And they observed a huge fluctuation peak at the melting curve, at the melting point, which definitely say that we have a second order transition. And they made a calculation, Ising model, and theoretically also support that. It's surprisingly, this transition in 2D, even melting, is of the second order. And we confirm this by measuring of hysteresis, when we typically ramp only up, but there were some, maybe half of the traces, maybe even more, where we return back to the lower temperature and made a full cycle. And indeed, at lower densities, we have hysteresis. So this is for these points. Very well seen. And at higher densities, this for these points, there is no measurable hysteresis. Second order. Another interesting thing which we maybe observed is a quadruple point. Because we have this triple point with liquid, normal solid, and gliding solid, but it might be also so that the transition from normal high density solid to liquid also go to this point. It's very difficult to measure here because two transitions are overlapping and is really difficult to say, to separate this. So this is very difficult region. But if so, we have a quadruple point, which is very rare phenomena in nature. And we all know the Gibbs phase rule, which saying that if phases are consisting from the same species, then there are only three, a triple point, only three phases can coexist. Well, maybe if this crystal here consists of dimers, then, and here it consists from Fermi monomer particles, atoms, so maybe it doesn't violate the Gibbs rule. So this would be very interesting to investigate and further. Recently, there appeared also theoretical paper in Nature Communications saying that the Gibbs phase rule may be generalized so that four phases can coexist, even in single component system. So that's, I don't know, just found this when searching for related literature. Okay, I have time still. Let's speak about a little bit about such a proposal that one could observe BAC, Bose-Einstein condensation of vacancy in our system. First, let me know that at low temperatures, the system becomes true one-dimensional. Orbital motion becomes frozen. The first excited orbital motion of vacancy has energy of 50 millikelvin about. So below 50 millikelvin, we have pure one-dimensional motion, so that vacancy delocalized completely here and may move only along the tube. Okay, then we can simply calculate the TC for the Bose-Einstein condensation. As usual, we should equalize number of particles or vacancies to this integral of the distribution function with zero chemical potential. And we obtain this formula, which actually diverges at long wavelengths as z to minus 1/2. And natural low energy cutoff must be set by the length of the tube, which is finite. So then length can come here to the low energy cutoff because there is a minimum possible momentum of this. And then we calculate it. It's very simple. And this gives 5 millikelvin if we take our length, our roughly estimated number of vacancies, and mass of vacancy equal to 2 masses of atoms. Okay. Now, what is very important, I was always saying that we have bosonic dimers, have bosonic dimer crystal, and then the vacancies must be also bosonic. But even more than that, we need the spin of this dimer should be 0. Because if there is a spin, then the motion of vacancy cannot be easy. It should be accompanied with a spin current, which is not easy in such systems, because at these systems there is no effective way to transport spin. Fortunately, these dimers are indeed bosonic, and moreover, they have spin equal 0. This is similar to the well-known problem of ortho and para hydrogen, which we all know. And the basic principle is such that the total wave function of diatomic molecule, or dimer in our case, which consists of 2 identical fermionic particles, should be antisymmetric with respect to permutation of atoms. The lowest orbital state is symmetric, G equals 0, as one can see. Then the spins must be antiparallel so that the spin part of the system is antisymmetric. So S equals 0. The first excited vibrational state is G equal 1. It's antisymmetric. And then the spin part of wave function must be symmetric, which means that spins are parallel and total spin is 1. But this first excited state has a huge energy. This is about 50 Kelvin, this rotational oscillation quantum. So, and then it appears that in spite of the fact that the direct spin-spin interaction is very weak, so the exchange interaction is millikelvin, and direct dipole-dipole interaction is, of course, much, much smaller. But despite this, the ground state with spin equals 0 is protected by the huge quantum of mechanical rotation. Okay, I think I come to my conclusion. So mechanical properties of submonolayer helium-3 adsorbed on the nanotube were measured. Unusual soft and mobile solid state has been observed. The new solid phase identified as bosonic dimer solid with delocalized 0-point vacancies. And the proposal had been made for observing Bose-Einstein condensation in this system at low enough temperatures. Thank you very much for your attention.
Thank you. This was a brilliant presentation. Anybody who has questions, please, for example, raise your hand using the function. But while we wait for other questions, I might start by asking, in this picture, which was a few slides back about the hysteresis of the second order transition, or whether there is one, if you scroll back to that. Yes, thank you. So here it looks like in the in this super solid data on the right, there is some overshoot. Can you give a brief comment on that?
I think it's normal solid. I think it's for normal solid to the liquid. It's melting of normal solid.
Well, anyway, yeah,
okay.
Thanks.
Okay, then, yeah. I don't have idea on that. Sometimes a low temperature parts don't coincide, especially this peak here. Yeah, it's quite common that on the way back you have a little bit lower. I don't know. One possible explanation would be that there is always a mixture of phases. For instance, this would be a mixture of 1/3 solid plus liquid. And when you melt it, it's uniform liquid. And when you go back, your solid cluster may appear at a little bit different place and giving a different contribution to the tension of the tube.
All right. I think John Saunders has a question. Please unmute yourself and go ahead.
Yeah. Can you hear me?
Yes.
Yeah. So what do you, my question is this, what do you actually mean by normal solid? Because as you were giving the talk, I was thinking of the phase diagram of the first layer on graphite, two-dimensional graphite, which you didn't show. Which has this sequence of root 3, 1/3 occupancy, and then domain wall solids, and then incommensurate solid. So to by normal solid, do you mean incommensurate solid, or is there some reason why you believe that incommensurate solids are suppressed on the surface of the nanotube?
Yes, that's correct. On the plane geometry of graphite, the dimer phases may be not energetically favorable because the distance between two sides, between two centers of hexagon is a little bit smaller than the hardcore diameter of two helium. So then they maybe repel each other and incommensurate state becomes more energetically favorable. But due to curvature of the nanotube, the distance between neighboring helium atoms is larger by about 30%. And then it's well above the hardcore radius. That's why we think that on the nanotube, instead of incommensurate solid, the dimer phases are realized.
So can I just ask then, what's the status of that? You say you think, what's the status of that? Is this a conjecture with which to interpret your data? or are there theoretical calculations, which I believe people could easily do, of the phase diagram on nanotubes which support your hypothesis?
It's hypothesis which explains all our observations. For instance, this. I think this is a very strong argument that this is not incommensurate solid, because not non-commensurate solid, because incommensurate solid would also have phonons which was observed on the plane geometry of graphite graphite. Here we definitely have something else. So, of course, dissipation, even if it's incommensurate solid, it's more or less stiff and much have lower dissipation than the fluid. So every single of this observation maybe could be explained by something else, but not all together. So yes, this is our point. Just due to the curvature, the dimer phases are more energetically favorable than the incommensurate, because they take use of every potential minima of the carbon lattice, and at the same time, this distance in this case is larger than the hardcore diameter. So we didn't really make a calculation of the phases on the carbon nanotube.
All right, thank you very much. I think Jan has a question. Just please unmute yourself and go ahead.
Yes, hi Igor, I got maybe a couple of questions. So what is the binding energy for submonolar helium-4 atoms on nanotube?
What is, sorry?
Binding energy. Or for submonolar.
100 Kelvin, 150, something like this.
That's close to graphite and graphite. But I remember that only 8 layers of graphene give similar binding potential. So here I would expect much lower binding energy.
For nanotube, yes, of course, it's lower. Yes, yes, sure.
Okay, but we don't know the number at the moment, so I can't remember it either.
I also don't remember now.
Yeah, and maybe my second question is, you are considering one-dimensional phonons and one-dimensional phase transitions. I presume it's in the direction along the nanotube axis.
Right.
But wouldn't systems support two-dimensional phonons on the surface of cylinder?
No, this
perpendicular to the axis of the nanotube.
Yeah, I understand. The transfers of phonons are frozen. Yes, this we check. Yeah.
How does it work?
You calculate energy of phonons, suggesting some reasonable speed of sound, and you put the like length, the phonons wavelengths equal to the length of the circle of the cross section, and you obtain something like 5 Kelvin, I think. 5 Kelvin for the transversal phonon. It has too large wave vector, too short wavelengths. It should fit itself when you go around. That sets the boundary condition, and it gives you that the wavelength is too short for these temperatures.
Okay, thank you.
Okay, thank you. Are there any other questions, maybe? Well, I was going to. Okay, John seems to have another one.
Sorry. It's lovely. Congratulations on some very beautiful work. What's going on in my mind is, you've posited these particular class of domain wall solids where the helium-3 show this dimerization behavior, which is would be very exciting if it was true. Are there other possible candidate domain wall solids which you've rejected because they don't have this dimerization property? How unique is your choice of domain wall solid?
We really didn't consider the possibility of domain wall solid because, of course, it might be also the case. But this is the simplest picture so that there could be domain wall. In principle, this is the domain wall, if one wish, this mismatch line. But it itself doesn't explain the mobility and softness of this solid. So we need really vacancies. That's why we concentrate on this simple model. Of course, in any particular density, you don't exactly fit to any of these commensurate phases. So you have different like fraction of different solids or maybe liquid, and that's will of course contain domain walls, but we didn't consider them not to overcomplicate the consideration. Of course there are, yeah.
All right, thank you. I might still entertain myself by asking, unless there are, well, I don't see any other questions. So I might entertain myself by asking, did you exclude any other simple explanations for what you're observing in the process of the experiment, which would be interesting for the people listening?
Yes. There was at some time the idea that it might be just a sliding of usual solid, just solid which is pinned at some conditions, and at some conditions it's not pinned. But it was very difficult to imagine that it is pinned at high temperatures, but it is unpinned at low temperatures. So, I mean, if it would be just normal solid, which is pinned here and unpinned here, this is very difficult to imagine that it becomes unpinned at low temperature. One would expect another, like vice versa. So you would have pinned here with high stiffness, and then unpinned here, which would look the same as, for instance, liquid. And another thing is that pinning, unpinning, if I'm talking about this possible explanation, is not in fact the transition. It's rather smooth crossover. So, and we wouldn't observe so nice and sharp transitions in this case. It will be very wide transition. So this consideration. And as I said, this solid, even pinned or unpinned, it would show phonons. So this soft mobile solid does not support phonons. So it's not even elastic. Okay, maybe there are phonons, but very little compared to the normal solid situation. So altogether, there was one more reason, I forgot it now, that we excluded this normal solid which is pinned or unpinned, and thus giving this strange behavior. So we end up with a dimer model, which is only one which explains all we find.
Okay, thank you. I think John, if I'm not mistaken, has a third question. Go ahead.
Well, it's a point of information, really. As you may know, we've had some interest in whether you can get a supersolid in 2 dimensions. And as part of this activity, we did some measurements on the submonolayer film of helium on graphite, and we looked at both helium-3 and helium-4. And in the case of the submonolayer film, we found behavior that was actually quite different from in the second layer. And it's well described, in fact, by an internal friction model. So you observe changes in both the frequency and the Q. So it looks like a sort of a decoupling or a change of stiffness. And of course, if you measure both the real and the imaginary part of the response, then you can compare it with some simple Debye model. And that's what's going on. So there's temperature-dependent effects at fixed coverage in the submonolayer film. Now, this may or it may not be related to what you've observed, but I just thought it would be interesting to point it out, and maybe we can show you the data at some stage.
Yeah, thank you. Thank you.
Igor, maybe you tell a bit about the amplitude dependence of the results, because this is one of the arguments against having this kind of deepening behavior.
Which results, sorry?
Amplitude dependence.
Oh, yes. Returning to this deepening model, we would have a strong dependence on the transition temperature of the applied RF power, which we did not observe. So we varied RF power, let's say, from -40 to -70 dB, and we did not ever see that this transition temperature remaining sharp depends on the excitation power, which would be the case if this is a deepening effect. Yeah, thank you, Pertti.
Okay, thank you. Dima has the next question. Go ahead.
Hi, Igor. So
Hi.
How difficult is it to pick and choose the type of nanotube before the experiment? So I think, as I understood, so you picked some random type of nanotube. Well, you don't know really.
Yes, that's true. We cannot control this, but like 90% of nanotubes will fit the condition. So basically,
yeah. So probably if you well, the 12% nanotube, so you won't see this effect because you won't have topologically protected vacancies. Is that correct?
We did not expect anything like this. We just start measuring and observe this behavior. So we did not choose carbon nanotube because we did not know what to choose. So it should be a good nanotube with not very small Q factor. And yeah, that's it. No, there was no specific choice. I may say that we actually have 2 nanotubes measured in parallel because so many nanotubes were broken when installing them on the craster. So at some point I decided to connect 2 in parallel. And this has such a obvious advantage that we could measure 2 resonances at the same time when sweeping temperature, having twice more data. And at the same time, we might be sure that this is not something strange which happens to one particular nanotube, but we have two tubes which behave similarly. So, but they were just two tubes. Of course, we have chosen metallic tubes. Yes, we were trying to choose the tubes which are lowest resistance at room temperature. So this was the choice.
At this stage, as there may be some people who need to leave at this point, I will point out that the next seminar will be next week, so on Tuesday, given by Petri Heikkinen. And then I think John seems to have something to say in the chat, so I think you can probably also.
Oh, that's fine. I'm just pointing out a few things in the chat. That's all. That's fine.
All right. Thank you. Are there any further questions or comments? Well, if there are no further questions or comments, I think we can wrap this up here. I thank everybody for a very nice discussion about this intriguing presentation, and I will see you all in a week. Thank you very much.
Thank you very much, all.
Thank you.